Hello everyone, my name is Wang. I'm from Google. Today I'm going to talk about generalized end-to-end loss for speaker verification. Before I go to any technical details, first I want to introduce the applications of speaker recognition at Google. For example, on Android, we have two applications. The first one, we call it From Any Screen. No matter what app you are using, for example, News or Google Maps, or when you are on the home screen, you will be able to speak the keyword OK Google and wake the assistant. But if someone else speaks exactly the same keyword OK Google, he won't be able to wake the assistant. The second application we call it Voice Unlock. From the lock screen, you will be able to speak the keyword OK Google and directly unlock your phone. This will free your hand from typing the password. On Google Home, we also have an application we call it multi-user. You can ask questions like, OK Google, what's on my calendar? And the device will return events from your calendar. That's a personalized result. But if you have a family member and that family member asks exactly the same question, OK Google, what's on my calendar? The device will respond with personalized answer from that family member's calendar. Before you will be able to do speaker verification, first you need to enroll your voice. We ask the speaker to speak OK Google 2 times and Hey Google 2 times. These are called the enrollment utterances. Then we will store the averaged embedding vector of these enrollment utterances on the device. So let's talk about generalized end-to-end loss. The basic idea is that we use a neural network as an audio embedding technique. For example, for keyword-based speaker verification, first we run a keyword detector on the input audio sequence. We extract the keyword segment from the audio, which is usually a fixed length segment, for example, 800 milliseconds. Then we feed this fixed length segment into our neural network, which is a multi-layer LSTM network. We take the last frame, last layer output as our embedding vector, which we call the D vector. Once we have two D vectors from two audio input, we can compute the cosine similarity between the two D vectors. If that similarity score is larger than a threshold, we consider the two audio are from the same person. If that cosine similarity score is smaller than a threshold, then we consider the two audio utterances are from different people. Now we have the embedding and the score. We need to define a loss function such that we can train our neural network. So in 2015, the FaceNet people from Google proposed the triplet loss. So this is a very simple loss function based on three utterances or three embeddings. First, there is an anchor embedding, which is from an arbitrary utterance. Then we have a positive embedding, which is from the same speaker as the anchor embedding. And the third embedding is called the negative embedding, which is from a different speaker from the anchor embedding. Now we have a positive pair and a negative pair. We compute the distance between the two pairs. We want the positive embedding to be close to the anchor embedding because they are from the same speaker. And at the same time, we want the negative embedding to be far away from the anchor embedding because they are from different speakers. So our loss function is just a subtraction of the two distances. So this is a very simple and very successful approach because it correctly models how we want the embedding space to be. But there is one disadvantage, which is that it does not simulate the runtime behavior. So what do I mean by runtime behavior? Remember that we collect multiple enrollment utterances from the user, and we average the embeddings of the four enrollment utterances as an offline process. But the triplet loss didn't model this averaging process, so it's not end-to-end. In 2016, our team proposed the tuple-based end-to-end NOS. The input to the NOS the input to our training is a tuple of utterances. Most of the utterances are from speaker A. We feed these utterances into our neural network and get the embeddings for speaker A, and we average these embeddings to get an averaged embedding for speaker A. There's one utterance from the tuple, which we call from speaker B, and we feed this utterance into the same neural network, get an embedding for speaker B. We compare this embedding for speaker B to the average embedding from speaker A and get a cosine similarity score. Then our problem is simply a binary classification, whether A is the same speaker as speaker B. So it's a same speaker versus different speakers binary classification problem. Because we are doing averaging of the utterances of the embeddings from utterances from speaker A. So this will simulate the enrollment process in our real runtime verification application. So this tuple-based end-to-end NOS was very successful because it exactly simulates what happens in the runtime. However, there is still one disadvantage, which is that because we are constructing tuples from the training set randomly, most tuples will be very easy. Thus, the training is going to be inefficient. So that's why in this paper, we are proposing a new generation of the NOS function. We call it the generalized end-to-end NOS. So consider one training batch for embedding EJI, which is the embedding from the I's utterance from speaker J. We want it to be close to the centroid of the true speaker, CJ. CJ is the centroid of all the embeddings from speaker J. And at the same time, we want EJI to be far away from the centroid of false speakers. Notice that both CK and CK prime are different speakers than speaker J. However, because CK is closer to EJI than CK prime, we only consider CK in our loss function. So CK is the closest first speaker centroid. This idea is like the max margin principle in support vector machine, and you can call CK the support speaker. We want EJI to be close to the true speaker centroid, and at the same time, far away from only the closest first speaker centroid. That's the idea of generalized end-to-end NOS. So we need to compute so many distances between embedding and centroid. So that's why in our batch training, we construct a similarity matrix such that each element in this similarity matrix is the cosine similarity between an embedding and a speaker centroid. Once we have this similarity matrix, we can define two different NOS functions, the softmax and the contrast NOS. You can see the paper for details. By some experiments, we find that the softmax works better for text-independent applications, while the contrast NOS works better for keyword-based applications. There is one trick about computing the centroid of the true speaker, which is that we should always exclude the embedding itself when computing the true speaker centroid. Otherwise, we are going to get a trivial solution, which is that all the utterances will have the same embedding. In the paper, we did some theoretical analysis on the efficiency between tuple end-to-end NOS and generalized end-to-end NOS. The conclusion is that if one training batch has n speakers, theoretically, one generalized end-to-end step is almost equivalent to 2 times n-1 tuple end-to-end steps, which is a huge efficiency gain. The part 2 of the presentation is about a technique we call it multi-reader. So the story is that Google wants to support 2 keywords at the same time, OK Google and Hey Google, and we want to use a single speaker recognition model to support both of the keywords. And the challenge is that our training datasets are very unbalanced. The OK Google training dataset has more than 150 million utterances, while the Hey Google training set has only about 1.2 million utterances. if we directly mix the two datasets together, we need to make sure that every training batch actually uses both the two data sources. However, that means that the batch needs to contain at least two speakers from each of the datasets. Let's make an assumption. For example, one training batch has about 32 speakers, which is a very reasonable batch size. In that case, we find that the probability that this batch has at least two speakers from the smaller dataset is only about 0.02, which is too small, which means that most of our training batches never make use of the smaller set, which is very bad. So that's why we are proposing the multi-reader technique. For each different data source, we extract the training batch separately from that source and compute the generalized end-to-end loss from that batch individually. And our final generalized end-to-end loss is simply a weighted sum of all the generalized end-to-end loss from each batch from each data source. That will make sure that every gradient we used to update our neural network parameters, the gradient covers all the data sources. The multi-reader technique can also be understood as a model regularization technique. For example, we have two datasets, D1 and D2. D2 is the smaller set, which is in-domain data. It's the dataset that we really care about. However, because it's too small, it's very easy to overfit on it. So that's why we use a larger dataset, D1, for our regularization term in the loss function. The multi-reader technique is not only useful for supporting multiple keywords, it's also very useful, for example, for supporting multiple gender group, age group, race group, and for supporting dialects and accented speech. Part 3 of the presentation is about text-independent speaker verification. So we are interested in identifying the speaker based on arbitrary speech rather than just the keyword. So the challenge is that the length of the utterance can vary, which is unlike keyword-based speaker verification, where we usually assume the keyword segment has a fixed length, for example, 800 milliseconds. The naive solution to text-independent is full sequence training. However, if we do full sequence training, because the length of the utterance can vary, so there will be no batching, which means it's going to be very, very slow. And we also need to dynamically unroll the RNN network, which makes it even slower. So that's why we are proposing sliding window inference for text-independent speaker verification. For a non-long utterance, we extract overlapping sliding windows from the utterance. These sliding windows have a fixed length, and for each sliding window, we run the LSTM network on them, on this sliding window, and get a d-vector output. For all the d-vectors from all the sliding windows, we first L2 normalize them, and then average them to get our final d-vector embedding of the entire long utterance. During the training of text-independent, we group the utterances by their length, such that every batch contains utterances with the same length with some minimal truncation. However, two utterances from two different batches can have different lengths. So let's show the experimental results. The first table is a comparison between multi-reader versus directly mixing the two datasets. This is for keyword-based experiments. We can see that no matter it is the same keyword verification or cross-keyword verification, the multi-reader equal error rate is significantly smaller than directly mixing the two datasets. The second table is a comparison between tuple end-to-end loss and generalized end-to-end loss, which is also for keyword-based experiments. We see that even when the neural networks have exactly the same topology and embedding dimensionality, no matter we are using multi-reader or not, generalized end-to-end loss is significantly better than tuple-based end-to-end loss, and at the same time, it is 3 times faster to converge than tuple end-to-end loss. The third table is for text independent. So we also did experiments for full sequence training. For full sequence, we use the softmax noise function, which is simply the multi-speaker classification problem. For example, you have like 100,000 speakers, then it is a 100,000 dimensional softmax, which means there are 100,000 categories for classification, and we use the layer before the softmax layer as our embedding layer. Okay, we see that full sequence plus softmax has very similar performance to tuple-based end-to-end noise training. However, tuple end-to-end noise is like 3 times faster to converge than full sequence training. Generalized end-to-end noise is significantly better in equal error rate than tuple-based end-to-end noise, and it is at the same time another 3 times faster to converge than tuple end-to-end noise. By using like larger training set and applying techniques like test normalization, we can get our equal error rate as small as 2.75%. So conclusions. We proposed generalized end-to-end noise, which is faster and better than traditional tuple-based end-to-end noise. There are other potential applications for this noise function, for example, face recognition. We proposed multi-reader, which is a very powerful technique for supporting multiple keywords, multiple like accented speech and like gender groups, age groups. We proposed the sliding window inference, which enabled tuple end-to-end and generalized end-to-end model training for text independent. So this year, our team has another 2 papers accepted by ICASSP. The first one is called Speaker Diarization with LSTM. We combine generalized text-independent model with spectral clustering and immediately get the state-of-the-art diarization system. The second paper is called Attention-Based Models for Text-Dependent Speaker Verification. We combine generalized end-to-end text-dependent model with attention layers to achieve silence robustness and noise robustness. Both of the poster sessions are Wednesday afternoon, so welcome to the poster sessions. Questions?